Yes, so thank you very much for the opportunity to give a talk here, and also to all the organizers for organizing this very beautiful program, and to IPAM and the people working for it for the help and availability. So today I would like to talk about some recent work on the Fermionic Gaussian free fields and connection to random lattice models, especially to Abelian sandpile models and uniform spanning trees. And this is a joint work with my former postdoc Leandro Chiarini, who's now in Durham, Alessandra Cipriani from London, and my current PhD, Alan Robert from Utrecht. Okay, so the plan of the talk for today is, so first I would like to introduce the Abelian sandpile model. So maybe some of you never heard about that, so it's nice to have a very light introduction and the connection to uniform spanning trees. Then in the second part, I would like to tell you something different, namely Grassmannian algebras, and define for you what I mean by Fermionic Gaussian free field. And in the third part, I would like to combine those things and show you how some cumulants of observables from the two first models can be expressed in terms of this Fermionic Gaussian free fields business. All right, so the Abelian sandpile model, so here's the picture. So the Abelian sandpile model was introduced by Bach, Tang, and Wiesenfeld in the late 80s, and it is as a toy model for displaying self-organized criticality. And self-organized criticality refers to statistical mechanical models which drive themselves in some sense into a critical state, which is typically characterized by power laws or, for example, correlation functions, without any fine-tuning of a parameter. So if you think of a classical Ising model which display a phase transition in 2D, you have to fine-tune the inverse temperature to let it go to a critical state, which is the phase transition state, and there you can observe some power laws or compute some power laws. Right, so, and the model is very rich because it has beautiful connections to, for example, spanning trees, Abelian groups, Tat polynomials. It is also known as the chip firing game, and has also some connections to log conformal field theories. And so just to mention some contributions from the physics and mathematics community to study this model from different angles. So this is far from a complete list, but I just wanted to flash some names who contributed to that. All right, so to be on the same page, let us look at like the very simple example and where I can introduce the model. So let us look at the 4x4 grid. Here I didn't display the edges, but here between the numbers there are existing edges. So it's a lambda. It's a subset of Z2, and at each vertex of my grid, I'm putting like a number, a natural number. Here the natural numbers are between 1 and 4. Okay, and so what is this? So this displays indicates the boundary, because at the boundary I'm wiring everything to one single vertex. Okay, so these internal vertices, they have 4 internal connections, but for example, this is a boundary vertex who has 3 internal connections, but 1 edge is connected to the boundary. And here 2 edges are connected to the boundary. Okay? All right, so this configuration we also call stable, because the height is between 1 and the degree, because each of the vertices has the same degree. And now what I want to do is I want to pick a side uniformly at random, for example, this one. And I'm adding a particle there. So because so this is also called the sandpile model, because these numbers can be sort of sand grains sitting on vertices. Okay, so here 4 sand grains sitting, or particles sitting on this vertex, and I'm adding another one, which makes now on this vertex like 5 particles sitting there. And the rule is as follows. So if the height or the number of particles at each side, if it's larger than the degree, then I call the side unstable and I'm toppling it. Okay, so I'm toppling it. How do I do that? I'm giving to each neighbor one particle, and I'm reducing the size of this unstable vertex by 1. Okay, so this one will receive 1, this one, this one, this one. Okay, let's do that. Then you see the configuration changed a bit. And now we have, okay, so this will become a 4, which is still okay, this is still okay, this is still okay, but you see we have now those two vertices which became unstable. So now what do we do? Suggestions.
Couple either.
Sorry?
Couple either one.
Either one. Will it matter? Okay, you know.
That's why it's called Abelian.
Okay, I gave it away. I should say sandpile model without Abelian. Right, exactly. So we have some experts in the audience. So we can topple indeed either one, because toppling order does not matter. So let's topple this one. And you see, since now, okay, so this one will receive one particle, this one, and this one. And since this vertex is connected to the boundary, which is wired to one vertex, which is also called a sink, you see that here one particle will leave the system and will leave the system, and the others will remain. So we have still this one and this one, which are unstable. So okay, I'm toppling this guy here. It has two connections to the boundary, so two particles will leave the system, and two will go here to the south and to the east. And okay, I continue to do that, and you see after a while I recover a unique stable configuration. So every vertex is again contains a number between 1 and 4. I'm stable, and I'm stopping the process. Okay? Questions?
So in the end, you lost something like 3 particles after.
Yes. Okay.
So this always this always compares to some stable.
Very good question. Exactly. Yes, it does. And why? The question is why? Because we have a boundary which acts as a sink. So we leave the possibility for particles to leave the system. So that's why it will always stabilize. So there are versions where you don't have a boundary, or you have different kind of boundaries. Then the question is a bit different. But here we have a boundary. So yes, it will stabilize. And you see, addition of a vertex here caused those 5 vertices to topple, and this is what we also call an avalanche. So addition of one particle caused an avalanche of size 5 in this case. Okay. Right. So this is just to fix some examples, and here let us now introduce this a bit more mathematically. So you can play this game. You can imagine on any kind of graph. So let's call. Okay, I call my vertex set W for a reason which will become clear a bit later. So our graph, okay, consists of some vertex set with a distinguished vertex, which I call the sink, which is the wiring, and a set of edges. And the configuration, the sandpile configuration is a map from this vertex set to the natural numbers, and we call it stable if it's smaller or equal to the degree. The dynamics is adding a particle uniformly at random, and then you do the toppling until you reach a stable state again. So this whole model you can describe in terms of a Markov chain on a finite state space, which is very nice because then you can also determine what the unique stationary measure will be. So let's call it mu, which will be the uniform measure on the set of recurrent configurations for the Markov chain. Okay. And this is very nice. So we are setting. So if we want to study, for example, avalanche sizes and so on, we are putting ourselves at stationarity and counting the corresponding amount of recurrent configurations. For example, if you want to estimate the amount of avalanche of size k, which upon adding a particle to a fixed site will always create an avalanche of size k.
What is an avalanche? It's the number of iterations you have to do until you stabilize?
The number of vertices which topple. Upon addition of a particle.
So in other words, the number of iterations you have to do until you are back into stable.
Yeah. All right, and this set is also very special because from group theory you can view it also as an abelian group. So with the operation of addition, it just means that, for example, I'm taking a recurrent configuration, I'm adding another recurrent configuration, and then I'm stabilizing everything. So adding means per vertex, so the heights per vertex, and stabilizing it, and then what I obtain is again a recurrent configuration in my group. All right, so if everything is determined by the unique stationary measure, right, then, okay, we have to have a way to compute a determinant, and actually the beautiful matrix tree theorem is telling us that the number of recurrent configurations is precisely equal to the number of spanning trees on this graph, which can be computed by this determinant. Okay, so there's a beautiful one-to-one correspondence between a configuration here and a spanning tree here, and I will show you in a minute how this goes. All right, so questions, for example, can be like depending on your favorite graph. What are, for example, what was the Holy Grail for a while, the avalanche size distribution, and showing that this obeys the power law. Determining the stationary measures also in some kind of infinite volume limits, because you can, this is of course for a finite graph, but you can ask yourself, can I construct an infinite volume measure by taking a weak limit of the stationary measures to infinity? You can ask yourself, you know, like stabilization questions if you remove the boundary, limiting shapes, etc. So what we have studied also is the odometer function. So this is a function which at each side will give you, at each time will give you the amount of particles which emitted from it upon stabilization. And based on this description of the odometer functions, for example, looking at scaling limits, etc., we were able to construct like an alternative way to constructing fractional Gaussian fields in an alternative way using this sandpile stuff. All right. Now, how to pass now to spanning trees? So here, let us start here. So this is an example of a recurrent configuration, and then here below, I want to display the spanning tree, which I will be creating by applying this Dar's burning algorithm. All right. So in the first step, I'm burning the boundary and all the edges connecting to it. Okay. So in the first step here, I don't have a boundary anymore. This border, this corner vertices have 2 remaining edges. These vertices have 3 remaining edges, and all internal have still their remaining edges. And what I do is I'm looking at the vertices whose height is higher than the number of existing edges. And in this case, you have those 4. So this is 3 because the number of existing edges is 2. Here the number of existing edges is 3, but height is 4. So those 4 will be my first candidates to be burnt. And they were burnt because I burnt the boundary. So I have to attach it. So this is the first step, to attach them to the boundary. Okay, but okay. So, think of the boundary being really wired to a single vertex. So in the end, this will be a tree which comes out, which has whose root has degree 4, because like there are 4 things growing out of it. All right, and now you see there are cases where it's easy to connect because, for example, this guy has only 1 connection to the boundary, so I'm connecting it via this. But those corner vertices have 2 possibilities to be connected, either via the south edge or via, for example, here the east edge, here north, and here. Okay, here actually just a little mistake. I took it from a paper. This should be here, but I will explain you in a while why. And here as well, so south or west. And for example, one common rule is to decide, because you have to make a rule to decide how to connect them, is that you take the height minus the number of existing edges. So here it will be 1. And then you go like in a circular way, like you connect to the first possible edge. So height is 1, I'm connecting to the first possible edge, which is the east edge. So I'm connecting here. Here is the same, height 1. Here I'm connecting to the first possible edge if I'm going like this way. Okay, here I don't have a choice, and here I should connect to the second possible edge. So this is the first. I'm going, so this should be connected to this one. Okay? All right, so this is...
Can't you just run also around the boundary and say that this 4 actually connects up because it's the second edge when I move clockwise around the whole boundary of the system?
Sorry, say again?
If I decided that my way of moving around was going around the whole boundary in a clockwise way, then the second available edge moving clockwise around would actually be the north edge, so that would give another rule.
But if I start here, and this is the first edge, and this would be the second edge.
I was imagining
Okay, you
around
start here.
like this.
You start here, yeah, then it fits, yeah.
But what difference does it make if they're all connected to the same vertex for you?
Because you want to be able to reconstruct them. Because you see, if here there would be 4, or here, then you would also burn it in the first stage, but you don't remember. Because here, if I give you this, I want you to be able to remember if this was a 3 or 4. Okay? Okay, so now the second step is, okay, so I have burned now those 4, and now again I'm doing the same, I'm asking myself the same question. Which heights of the vertices have height higher than the number of existing edges? So here you have 2 edges, you have 2 edges, height is 3, so that those will burn at the second stage. And how do I connect it to the existing spanning tree? Well, so this got burnable at the second time step because this one was burned. So I'm connecting this vertex, so yeah, this to this. I'm doing this for the other as well. So here as well, this was burned because this was burned, so I'm connecting it here to the south. This was burned because this was burned, and I'm connecting it to the west. And then I'm burning these 3, and then you see here I'm doing the same, so and so forth until in the end I remain with one particle, which, okay, height is 1, and there are 0 existing edges, so this will be burned in the last stage and connected to this guy in the north. Okay, so this is like a spanning tree again, where this wired boundary has to be viewed as a root, and then you have here 1, 2, 3, 4. 4 streams for like degree 4 of the roots from which the tree is growing. And there's also way back, so I will not have time to explain that. But so if I give you this, spanning tree, and I give you the rule under which I'm in cases where you can choose, where you decide how to connect, then you can go back and you can retrieve this configuration. Okay?
So this last number that you end with, this 1, could it have been anything else? Could it have been 3, 4?
Yes.
So it's like a 4-to-1 mapping? Or is there any significance to this last number?
So, okay. So I will talk about the leaves a bit later. Yeah, but indeed, it's not all the leaves have coming from height 1s. But, okay, yeah, I will talk about this a bit later. All right. Now, there's now this possibility to wake up again. Now we'll talk about something a bit different, because many algebras in the Fermionic Gaussian free field, and then in the third part I will connect it. All right. So I'm considering the following Riemannian algebra. So I have here, so lambda will be finite subset, which in my talk will be either subset of ZD or the triangular lattice. And I will look at a polynomial ring over R with like 2 cardinality of lambda generators. And each polynomial can be written as the product of these monomials and times some real number, ai, let's say. And the rule is that they cannot, so if I have, so this will only consist of monomials. So if I have the product of 2 of the generators, like the square of each of the generator will give me 0, and they are anti-commutative. And the derivation is defined in the usual way. So if I want to derive at the jth place of this product of monomials, well, this will be just a 1, and then I have to correct it by -1 of the number of swaps I have to do to get this guy like in the front. Okay. So if there is in this index set the j, then this is equal to that, and otherwise it will be just 0. And integration is also done in the usual way. So integration goes via derivation of with respect to all the generators. Questions? Not that, okay. From here. Okay, so now we will write, instead of the size, I want to write psi, so psi v and psi v bar. So I will have like a pair for each side in my finite lattice. I will associate a pair of generators. And the Fermionic Gaussian free field will be defined in the following way. So a state with respect to this polynomial ring is just a map which takes a polynomial and spits out a real number. And it's the Fermionic Gaussian free field is just the normalized state under this rule, let's say. So I have here derivation with respect to all the generators of the exponential of the inner product here of all my generators. This is the just normal graph Laplacian with Dirichlet boundary conditions. Here is the other pair of the generators, and I'm multiplying it with f. And I'm normalizing it by, because so if I'm want to have like a normalized state to it's not really probability, but you want it to resemble something normalized, because I will match it to a probability later. So I'm normalizing it by 1. So if I replace the f by 1 and this under this measure, under this rule will give me just the determinant of the graph Laplacian. Okay, this is just a simple fact from the Wick theorem, which tells you if you have just here an M times M matrix with real coefficients A, then this whole thing will be just giving you the determinant of this matrix.
Could you comment why it's called Fermionic Gaussian free field? Like, what's the terminology?
Yes, very good question. This will come in 2 slides. Okay, then some examples. So let's say F is just this product of this pair. Then so evaluated here under this Fermionic GFF state, this would just give me the Green's function with Dirichlet boundary conditions at VV. If you take a product of 2 pairs, then this will give me the determinant of those Green's function. And if you just rewrite it in a covariance type of way, you see that they are like negatively correlated. And now here, to answer your question, so why the name is, so remember, okay, so the Fermionic GFF, we define it as a state acting on these polynomials in this way. So if this is the normalization, and this is the interaction, the Gaussian interaction, and if you just compare it to the density of a classical GFF on a lattice, say, on lambda, just subset of ZD, then you see they're in some sense very similar. So you have here this exponential interaction part, which is very similar to this one. And okay, the difference is here in the normalization. Okay, apart the constant, here you take the square root of the determinant, and here you take the determinants. So it's not really the same, but it's very close to it.
And why the word fermionic? Like just the word fermionic, where does it come?
Yeah, because it's built on this fermionic states, because those are generators of my polynomial ring of this Grassmannian algebra, and they're anti-commutative. And yeah.
Aren't they like creation and annihilation operators?
Yeah, it corresponds to that. Yeah. Okay, so what we will look at, not the k-point functions, but cumulants. So here's just the cumulant generating function for multivariate variable. And we will look at the joint cumulants of first order coming from this cumulant generating function, which is just take this kt and take the derivative with respect to all the tn's equal to 0. So this is really so this is corresponding to this thing for m equal to the 1, 1, 1, 1 vector. And like just an example, if you take 2 pairs, then this will give you the covariance. And in general, you take, for example, 3, x1, x2 is 3, then will be giving you, this will give you the product over the k-point, the expectation of the 3 product, and then all the combinations of 2 and 1. And there's a formula to go back from, if you're interested in like k-point functions, then with the summation formula, you can get this from the cumulants. There's another formula also for the other way around. So if you have this, then you can sum it in terms of cumulants. So it's somehow like one So there's some mapping between the cumulants and the k-point functions. All right. Now, what kind of probabilistic observables I want to look at? So I want to look at the height 1 field of the RSM. So the height 1 field is here. This is just the indicator, the random variable, which is the indicator that at the site V, the height is 1. So this will give me a 1 if at the site V really there's only one particle, and 0 if there's 2, 3, 4, or more particles. It's a very simple observable. And I also will look at the degree, like an average degree field of the uniform spanning tree. So this is just, okay, per vertex, I'm looking like what is the random degree of my spanning tree, and I'm normalizing it by the degree of the vertex. And the corresponding fermionic observables I want to match it to are like this. So I'm taking first I call XV, which is just like an averaged sum over products of gradients. Those are discrete gradients of the two pairs of because remember I'm putting two pairs at each vertex. So this is the grade. So it's like a product of two gradients of these two pairs, and then I'm in all the directions of the vertex, and then I'm averaging over it, and then I need like some, okay, I call it corrector, and I will explain to you why I call it corrector a bit later, which is just the product over all the directions of 1 minus this thing. Okay? Okay, so let's put them together. So on the one hand, we have, for example, let's take the simple case that I'm just looking at the origin. I'm looking at the probability that at the origin I have one particle. Okay? There's a very nice theorem which is telling you that, well, this probability you can express in terms of spanning trees, namely that there is, okay. You also, for example, you have 2D. Then you say that, okay, let's call this E, and this F1, F2, F3. So let's fix one of the edges, and I don't care which one. Then this probability will be the same as the probability that in the corresponding like in the spanning tree, those edges are not there. Those edges which are not equal to E are not there. Okay, like 3 edges apart 1. And the nice thing is that I don't care which one it is. So here I'm fixing this one, but it could be this one, or this one. And so if you know also a bit about uniform spanning trees, you see immediately that this can be expressed as a determinant of the identity minus a matrix which is consisting of those 3 edges which are not there, the double gradients of double gradients in directions of the edges which are not there of the Green function. Okay, so let's say I'm just taking E1 like this to be my E. And then you can like compute this thing. So okay, here I call it F or E1, E2, E3, doesn't matter. So you can by inclusion, exclusion, you can express this probability of this thing as this. So it means that as the probability that this chosen E1 is there minus probability that this is there and another one is there in the spanning tree, which is not equal to E1. Here you have triplets. And you're summing over all possible I and EJ. And here you have minus all the possible edges are there. It's just simple inclusion, exclusion. But okay, but just remember, okay, like probability of this chosen edge is there, minus some couplets are not there, plus triplets are there, minus all the 4 are not there. Okay, now let's look at on the fermionic side. So you see, if I'm looking at my corrector term, and I'm just let's replace this term by AI for simplicity, and let us just write out this this product, and keeping in mind that squares give me 0 contributions. Then you see, okay, this will give you 1. This will give you sum over all the singles, all the single 4 directions, couples, triplets, and plus like all the 4 of them. Okay, and now let's take the product of those two. If you take the product of those two, then you see, okay, you have like some averaged Okay, so product of two is the definition, and then what you will get if you just write this out is you have like an averaged sum over all the single ones minus the couples plus the triplets and minus all the 4 of them. So now it should be, aha, this is not coincidence. No, it's not. So indeed, let us use this very beautiful observation by Bauer, Schmidt, Crawford, Helmut, and Swan, which is telling us, well, so you can express, for example, the probability that some edges are in the spanning trees in terms of this fermionic calculus and the fact, this fermionic state evaluated for this F, which is, for example, this is there, this double gradients in this direction are here. Okay, so if we use this and just replace everything, then we get that, oh, this probability is precisely the same as this thing. Okay? So in some sense, this is taking into account edges which are there, and this is taking into account some edges which we want not to be there. All right, so this is like for a single point, and this you can easily you can generalize to like here like a k-point function. So if you take set V, which is a subset of lambda, and we call it good set, which just means that I don't allow neighboring vertices, and I want to be a bit far from the boundary. So I cannot be close to the boundary, and I cannot have neighbors. Otherwise, this thing is 0. So if I'm in this case, then the k-point function of this height 1 variables can be written in terms of this fermionic state, the k.1 of this xv and yv, and for the degree fit of the uniform spanning tree, you get like something very similar, but you see this corrector thing is not there. Okay, so here we notice that the height 1 and the degree fit can be expressed as squares of the local observables with respect to this Fermionic Gaussian free fields and in terms of this Grassmannian algebra formalism. And let's go a little bit further. So, okay, the main ingredients, just to tell you very quick, is like this observation of that the probability that some edges are in the spanning trees can be expressed as a product over those edges, double gradients of this size under the fermionic FGFF. Then some very nice work by Caracciolo, Socas, Protiello. So this Wick formula for these things. And here we will get like determinants of the graph Laplacians and of these double gradients of the Green's function. And yeah, so and this observation from the sandpile part that you can express this k-point function of the height 1s as probability that you fix some edge and some edge incident to each of the vertices, and then you have that all the other parties' edge are not in the spanning tree. And this you do for every of the vertices in V. Okay. Now, so how does this formula, this cumulant formula, look like? So for the like on the lattice, so this doesn't depend really. So this is very general. This is true for any like discrete lattice. So we can express this in terms of these constants. Then you have here. This is like just some combinatorial thing, and then over permutation of connected. Those are connected permutations of edges. So what does it mean? So if you have, for example, 2 points, okay, then like, and you look at these, so this is not allowed because it's not connected. Oh, oops, yeah, okay. So you can have here, you can have here, and this is allowed. Okay, so you want to connect the points, because those will be remaining here. And we computed the constants, so this is like some complicated formula with these constants for the 2 different lattices. And here the same for the this degree field. Here already the formula on the discrete level looks a bit nicer and much more close to the formula which we get after the scaling limit. So here I'm summing over cyclic permutations of the vertices. This is just a map which assigns to every vertex like one of the independent directions. And here I have a product over the double gradients of the Green's function. So this is coming from the from this MS matrix before. Okay, and like this maybe becomes a bit more interesting. So here we are looking at the scaling limit. So take some subset of RD and like discretize it. So here L will be ZD or the triangular lattice. And then if you scale this cumulants by n to the d, which depends on the lattice, so d for ZD and 2 for the triangular lattice, then you will get that this cumulants will converge to this formula. You see this is much closer to the discrete formula of the uniform spanning tree. So you have here cyclic permutations of the vertices, and here you have all the combinations of mapping a vertex to one of these independent edges. And here you have the continuum Green's function in this domain with directly boundary conditions. And we computed, we have a formula for this constant which depends on the lattice, and we computed it explicitly for Z2 and for the triangular lattice. And the nice thing is, so I'll tell you in a moment, that it fits like some prediction which was done from the physics community, and you can relate it to the probability of having height 1 in like the infinite volume in the origin, for example. Okay, so this is pi times this probability on Z2, and this constant for the triangular lattice is, okay, this correction terms times the probability, which is like a very long expression for the height 1 probability on the triangular lattice, which we also know. Okay, right. And here this is for the uniform spanning tree. And then if you see here, the formula is precisely the same. So the structure of the uniform spanning tree, apart the constants, you see, so you have cyclic permutation, you have these maps, and you have these products over the double derivatives of the Green's function. And here this was for the height 1 field, so cyclic permutation, maps, Green's function. So apart these constants, they are precisely the same. And now maybe this explains why I call this y variable a corrector, because the structure really comes from the x, from the products of this double gradients of my psi's, and this other term is contributing to the constant here. Okay. Right. Okay. So remarks. So we were able to find an explicit formula for this cumulants and the scaling limit for this height 1 field in terms of Grassmannian variables. So the nice thing is that the structure of this cumulants in the scaling limit for the UST and for the height 1 field is the same up to constants. So the final formula for the cumulants in d equal to 2 was already computed by Dörre in 2009. But it was done by very heavy computations, just manipulating the determinants, and not linked to this object. So we linked it to this object, and then could confirm that we got the same formula. What also Dörre proved is that actually the limits of this cumulant, so let's just denote by small k, the scaling limit of the cumulants for your height 1 field is conformal covariant with scale dimension 2. Okay, so this for some conformal isomorphism map, this will satisfy this equation. So since you see the structure, so if you look at the cumulants of the UST and you rescale it by the correct constant, then the cumulants will be the same in the limit. So this will then, a fortiori, will also hold for the UST. And so the nice thing is that so this goes to supporting the conjecture by Philippe Ruel that the height 1 field can be described by symplectic fermion theory. So he wrote the primary field of Ruszel having this form. So this is minus C/2. And this C constant is the same as we get for the cumulants. And here you have, so theta is the free field. And this is the conject. Yeah, this is also another copy of the free field. So you see here you have the structure consists of products of gradients of the free field and multiplied by this constant. So yeah, so it supports, since also we match bits, so we match the structure, we match this constant, it supports the conjecture. And yeah, what is still open in future work? So like universality in the scaling limit, because we were looking at the cumulants on ZD and on the triangular lattice, because they're nicely and regular, but of course, it would be very nice to have this for any general lattice with conductances, what we are currently looking at. Then also the big open question, scaling limits of cumulants of higher heights in general observable. This height 1 is also in some sense special. It's very local because it can be described by leaves of the spanning tree, but other heights a priori not. And what is, big open question also to construct really a lattice symplectic fermion theory, which we are also looking at, and match the cumulants. And very important and beautiful work in this direction is by Engler, Kitteler, Wiklund, and David was here. Ask him, De La Besat and also Kitteler, recently for, this is for the GFF, this is for the Ising model, and like general other lattice models and match it to lattice CFTs. So let me just give you some references. So if you want to see more and look at the computations, you can look at our articles. This is the one where Dürre for the first time computed the conformal covariance of this height 1 field and obtained this cumulant formula for Z2, but by different means. And now, like, these were very nice articles which we consulted as a reference, and then those were just 2 lattice CFTs, which I mentioned, which I would like to give attention to because I think they are very nice. Okay, thank you very much.